first thing that I usually do is I like type these two equations in. And you want to be really careful and make sure you type them in correctly, because if you type them in wrong, you're going to get everything wrong on those. All right. So y'all, well, that's a crazy graph. Y'all make sure I've got everything in right. And in fact, I would probably go ahead and do 0 less than t less than or equal to 12. That way you will only be looking at the part that you really need. And g of t equals 3 plus 2.4 natural log of t to the second plus 2t. Okay, so I would go ahead and like type those in from the beginning. The grocery store opens. It has 50 pounds of bananas on the display table. I mean, they were just asking for there to be memes about this whenever they decided that bananas on the display was what they were going with here. Seems like no grocery store in the world is actually doing this, but this is what they've done. Customers remove bananas from the display table at a rate modeled by F here. And after the store has been open for 3 hours, store employees add bananas to the display table at a rate modeled by this function right here, where g of t is measured in pounds per hour, and t is the number of hours after the store opened. For A, it says how many pounds of bananas are removed from the display table during the first 2 hours the store is open. What do you guys think? Okay, of which function? F of t. So all you have to write for this is integral from 0 to 2, f of t dt, and then you are going to go over here, integral from 0 to 2, f of t dt, and we're getting 20.051. And they did not specifically say to give the units on this, but I would in every scenario just in case there was, usually they're going, if there's a point for it, they'll tell you to do units. But what is that? 20.051 what? Pounds of bananas. Okay. B is a little bit of a different question. We haven't seen one quite like this. It says find f prime of 7. Using correct units, explain the meaning of f prime of 7 in the context of the problem. So finding f prime of 7 is super easy because this is a calculator active question. You're going to write down f prime of 7. You're going to go over here to Desmos. You're going to type in f prime of 7. As long as you got f in there, it should give you the right answer. You get negative 8.11. I'm going to go 1195. I don't like having to round where you got to, it could be 120, but I don't like rounding like that. So this problem was probably, this is probably worth 2 points. Yeah, and no, let's see. Yeah, 2 points, and f prime of 7 is one of the points there. So, so that's an easy point to get right there. The meaning not as much. Okay, what is f of t? What does that give you? All So F of T is the rate bananas are removed. And what are the units for that rate? That is pounds of bananas per hour. Okay, so that's F. That's given to you in the problem. We're talking about F prime. So if we take the derivative of a rate, what are we going to get? Pounds per hour, pounds per hour squared. Yes. So this is the rate at which the rate is changing. So anytime you're explaining this, first of all, if it's at a point, you want to say at time t equals 7. You have to put that because this is not just in general. This is at the specific time. So at time t equals 7. The rate of change of the amount of bananas is it going to be increasing or decreasing? Decreasing, since we got a negative, is decreasing, and this is very important. The rate of change is decreasing at a rate of 8.1195 pounds per hour, or you could say pounds per hour squared. So when you're talking about a derivative of something that was already a rate, you need rate of a rate. So that like word rate should be there twice for that. Because we use the word decreasing, we don't want to use the negative whenever we talk about that value for that. Sometimes right here, they say find the integral from 0 to 6 and tell what it means. If you integrate F, what would you be getting? Just pounds. It's just the amount of bananas, right? So you need to just know in relation to where you're at. They usually give you, the equations they give you are usually the rates because they can ask you to take a derivative and they can ask you to integrate in the same problem. So sometimes they'll give you either the second derivative or the original, but usually it's that rate that they'll give you for these. Okay? C says, is the number of pounds of bananas on the display table increasing or decreasing at time t equals 5? Give a reason for your answer. What do you guys think? Right.
You want to subtract F of 5 from G of 5, see whether or not that
Okay. All right. That'll work great because those are the rates at which bananas are added and taken away, right? Another option, so just to give, because the key does it that way, I'm going to do it just a different way. So like if you do F of 5, that gives you the rate that bananas are being taken away, right? So F of 5 equals 13.795, and then G of 5, we got G is 11.533 right there, and both of these are bananas, or pounds per hour, sorry. Pounds of bananas per hour. So this is removed, right? And this is added, right? So another option for this, so what Joshua said where we have, like, you could do f of, or g of 5 minus f of 5 and see if it's positive or negative. We also could just look, bananas are being removed at a rate of 13.795 pounds per hour. They are being added at a rate of 11.533 pounds per hour. Therefore, you're removing more than you're adding, so your number of bananas should be decreasing, right, at this point. So I would say since the rate at which bananas are removed, actually I would start with at t equals 5, so we know we're talking about at this point, is greater than the rate at which they are replaced the number of bananas is decreasing. At t equals 5. You've got some other options, though. You can look at g of 5 minus f of 5, say since it is negative, the number of bananas is decreasing. You could, at this point, go ahead and write your equation for the number of bananas, and then take that derivative, which is going to end up being g of x minus f of x, and like look at it that way. You don't have to do it that way here, but it will help you on D. You already have part D done if you do it that way. Okay, questions? Okay, and D says how many pounds of bananas are on the display table at time t equals 8. Okay, so if we're looking for number of bananas, so I'm gonna call this B of t. It's a good idea if you like introduce a new function, label it and tell them what it is. So this is number or pounds of bananas on display. So what would our equation look like here? And actually, I'm not going to do B of t, I'm going to do B of 8 because they really only asked us about 8. Yep, that's going to be part of it. Okay, so we started with 50, right, because it tells us when the store opened that there were 50 pounds of bananas. It says that somewhere right up here at the top. So we start with 50, okay, and then bananas are taken away and bananas are added. We're minus the taken away, right, so we'll integrate from 0 to 8 f of t dt. And then we have to add the bananas that are added. What would that interval look like? What are my limits on that? No. It is 3 to 8. Why is it 3 to 8 instead of 0 to 8? They don't start putting bananas back until 3. So if you integrate that from 0 to 8, you'll get the wrong answer for that. So that's a little, it's not too terrible, but it's a little trick that I think you're probably pretty likely to mix up there, because that's not been the case on a lot of the other problems that we looked at. So we can just type this in, 50 minus the integral from 0 to 8 of f of t dt plus the integral from 3 to 8 of g of t dt, and we get 23.347 23.347 pounds. Okay, are these starting to make a little more sense? Like, it's helping, hopefully, the others. Okay, so we got dy equals y squared dx. You'll need to divide by y squared. So you could leave it like this if you want. Here's the danger with that. This is wrong, so don't do it. But here's what kids want to do. Like, they want to integrate both sides, and they want to say natural log of y squared. Right here. Because you got y squared on the bottom. That is not right. You do not want to do that. So what I would do instead, it's only 1 over x or 1 over y that when you integrate it, you get natural log. If whatever's in the bottom is raised to a power, then it's not a natural log. So I would write it this way instead. Let's put it up here. I would do y to the negative 2 power dy equals, still have our integral symbol, equals dx. So then when you integrate, you do y to the negative 1 power. You divide out front by the negative 1. So you get negative y to the negative 1 equals, over here, what do we get when we integrate dx? Just x. And what else do we need? Plus c. Can't forget that plus c, because if you don't have the plus c, you can't plug your initial condition in to solve for anything. So at this point, I would definitely rewrite this as negative 1 over y equals x plus c. And it is up to you whether you want to find c first or whether you want to solve for y first here. It's really, I would say they're equally easy on this one. So let's find c first. So we got negative 1 over 1 equals 1 plus c. So negative 1 equals 1 plus c. Subtract that 1, you get negative 2 as your c. I'm going to move over to the left-hand side here. So that gives us negative 1 over y equals x minus 2. Okay. Now we need to solve for y because all of these equations are solved for f of x, which is like your y. So what should we do? Can't solve for y while it's in the bottom, so you got to multiply by y. Make sure you put some parentheses right there. So negative 1 equals x minus 2 times y. And then divide x minus 2. So we're getting y equals negative 1 over x minus 2, which is not an answer choice here for this one. So whenever we look at this, I've got two options basically, and then I got to think about domains for this. So which one, either A and B or C and D, which one's going to match this? It's C and D. And all we got to do is like multiply top and bottom by a negative, right? So if we multiply the top and bottom by a negative, we'll get a 1 on top, and we'll get negative x plus 2, which we could write as 1 over 2 minus x. So that definitely rules out A and B. And then we have to think about our restrictions on our domain, which is what makes this one even more difficult here. So definitely, I cannot plug 2 into this problem. Why can I not plug in 2? 0 in the bottom. So it could be C or it could be D because this is x is less than 2. When we're talking about differential equations, when you have a value that like your x value cannot be, in your like slope field, if you're thinking of a slope field, you're going to have like an asymptote there on that slope field. It might be a slant asymptote, it might be horizontal, it might be vertical. It depends on what type of function you're looking at. But your solution can't really like cross that gap, right? So when I know x definitely cannot equal 2, but it also can't be less than 2 and greater than 2 at the same time. So I got to pick one. In this case, obviously it's going to be x is less than 2, but that's only, like, if there was an option of x is greater than 2, we wouldn't know what, we would need to know more, right? So you need to look at your initial condition. So when I plug in 1, I need to get a positive 1. So in this case, I've got 1 over 2 minus 1. Actually, no, I don't need to. That'll work. That will work because of the way we set it up. But when I plug in 1, I need to get 1. And the number that I'm plugging in is 1. And so, while since x cannot equal 2, that means either x is less than 2 or x is greater than 2, right? And we've got to pick one of those. So since this number right here that you're plugging in is 1, you want to pick the part where that number falls, right? And so this is a 1. We're going to pick the x is less than 2 because 1 is less than 2, and D is going to be our answer. Okay, so like it's kind of similar to what we were doing up here. Like for number 3, C and D are not going to be your answers because when it has the absolute value bars, that means x is greater than 3 or x is less than -3. So for a particular solution problem, it's not going to be your answer. So like in this case right here, the number you're plugging in is -5. -5 is less than -3. So that ends up being, you know, what you choose for that. Does that make sense? That always throws me off a little bit whenever I do these problems, but it is something you're supposed to consider. All right, let's look at C, part C for this one here. We are supposed to find the particular solution, y equals f of x to the given differential equation with the initial condition of 3, 1. So the function needs to be separated first. And so if we multiply by our dx, then we got this over here. We'd have to multiply. This one's a little, I really just went crazy right there solving that and didn't show much work. But multiply by dx. So then you got dy equals 2 minus y. In fact, I don't really know why I did it the way that I did it there. What I would do now that I think I know more than I did then, I would multiply by 1 over 2 minus y right here and cancel that out. 1 over 2 minus y right here. And then that's going to give you 1 over 2 minus y dy equals 1 over x dx. Everybody okay on separating? Then I think what we like get in the habit of doing here is you like automatically, oh, I got stuff on the bottom, natural log, right? Whenever you integrate. But you have to be careful over here because you have to do a u to u on this side. U is 2 minus y. So du is negative dy. So you have to add in a negative right here with your dy, which means you got to put a negative out front. So you get negative natural log of 2 minus y equals natural log of x plus c. Technically, that should have absolute value bars there too. Yeah.
What is it that it is just natural log? What is that?
Just like 1 over x will be a natural log, but you do always need those absolute value bars there. They usually end up going away later in the problem, so it's one of those things you might could get away with not putting them there, but they do technically have absolute value bars on them there. And like a lot of times what we see is like if you're integrating, for example, 1 over x plus 7 dx like that, it is a UDU, but it ends up looking like it wasn't because it, like the derivative of x is just dx, so you don't have to add anything else in. Be really careful if it's not like just x plus or minus a number. You're going to have a UDU that you got to adjust there. Because that negative is usually like the biggest thing I see on a problem like this. People forget that negative right there. Now, you've got options on what you want to do, on whether you want to solve for, like in my, looking back at this problem, there's so many things I would do. Like, I almost think I'd solve for y first before I find c. You can do either way. So what I did is I found c first. So I took the point 3, 1 and I plugged it in. 3 goes right here, 1 goes right here. You get negative natural log of 1 equals natural log of 3 plus c. What is natural log of 1? It is 0. So this right here is 0. And then the natural log of 3 gets moved to the other side. So you get negative natural log of 3. So if you put that back in for your c, now we've got negative natural log of 2 minus y equals natural log of x minus natural log of 3. And that negative out there is kind of an issue because if you try to do e to the power, it's going to keep that from canceling. So I divided everything by that negative 1 there. And so if I do that, my natural log is negative, my natural log of x is negative, my natural log of 3 is positive. Now, I switched the order just because I didn't want to have that negative out front. And these can be combined using properties of exponents. So this is going to be natural log of 3 divided by x. And so at this point, you can do e to the power on both sides. You get 2 minus y equals 3 over x. And then you subtract your 2 and divide by your negative, and you will get y equals 2 minus 3 over x. Right there. Let's look at what that one, oh, gracious. Just trying to give myself some room. Let's do this. Insert. Page break. There we go. All right. Let's pick up at like this point, and let's look at what it would look like if you solve for y first instead. Negative natural log of absolute value of 2 minus y equals natural log absolute value of x plus c. So, if you solve for y first, you're trying to get that y by itself. It is a problem if you've got that negative right there. So, it's still going to be a little bit of a problem, but I would divide it off. So, I'd have natural log of the absolute value of 2 minus y equals negative natural log absolute value of x plus c. Now, I could put minus c there. Do I have to put minus c? C is an unknown quantity, so it doesn't really matter whether it's plus c or minus c, because you could just change the sign of whatever c is. So I usually just work with the c like it just absorbs whatever happens to it. Like divide it by negative 1, it's still an unknown quantity, so I don't change it. Now, you've got an issue because this negative is out front. What could you do with that coefficient? It's like a negative 1. What could you do with it? If I divide it off, it goes back over here, which is where I tried to get rid of it from. It can go in as an exponent. So I got natural log absolute value of 2 minus y equals natural log of absolute value of x to the negative 1 plus c. So now I can do e to the power on both sides. And over here, I just get 2 minus y. Right here, this c is going to go out front as the coefficient. E and natural log cancel, and I get c times x to the negative 1. I don't have to have the absolute value bars anymore because the c takes care of that for me. And so I would subtract 2, negative y equals cx to the negative 1 minus 2. I would divide by negative 1. So y equals, technically it's a negative c here. Does it matter if it's a negative c? C's unknown, so I would just leave it a c, x to the negative 1 plus 2, right there. If you want to make it a negative c, it can still work out. It's fine. It's just less you have to worry about in the next step. And so then, if you solve it for y first, then plug in your coordinate. The coordinate you're plugging in was 3, 1. Yeah, 3, 1. So you got 1 equals c times 3 to the negative 1 power plus 2. So that's 1 equals 3 to the negative 1 is 1/3 plus 2. So you can subtract that 2. Negative 1 equals 1/3 c. You could multiply by 3 on both sides. Negative 3 is your c. So y equals negative 3x to the negative 1 plus 2. Or that could also be written as y equals negative 3 over x plus 2. Which that is what we got. Well, we had it written as 2 minus 3 over x, but those are both fine. That little negative out there is what kind of makes that one harder. It's a little easier if it doesn't have that negative right there. I don't really know that it's necessarily easier either way, whether you solve for y or plug in your point first. You can do either one. All right, questions here? All right, let me know. All right, so differential equations have all kinds of cool applications. And I did want to show you this. I added this to, oh, I might have messed it up though. I added this to Canvas, even though if it's an ed puzzle, I may have to go back in. I've got to go back and reassign this like to you. But there's a video from Ed Puzzle. This link's probably not going to work because it's old. But there's a video that they did like at the very beginning of COVID. These guys from this like YouTube channel called Numberphile, where they'll go into like a lot of different math sort of things, sort of explained how differential equations could be used to like track those curves and stuff. And it's really interesting. It's about like 20 minutes long. So I got to fix the link, but it's going to be on Ed Puzzle. And when did I put the date for this? Did I put a date? Oh, I don't have it set like that. But we'll say whenever I decide to make Unit 7 test corrections due, same time as Unit 7 test corrections. You guys know enough about differential equations now that you should be able to follow what they're talking about somewhat. Now, they go into multiple variable stuff, so it's a little bit more complicated. Like, you wouldn't be able to actually work it all out, but you can kind of follow what they're talking about there. So, I will give you 5 points on the test if you watch that Ed Puzzle video there. So, it will be, I'll fix the Ed Puzzle link. It's on Ed Puzzle, so I can make sure you really watched it because it doesn't let you cut it off. And I think there might be a few. They're not like, it is like a little over our heads a little bit, so it won't be like calculate this. It'll be maybe like, what's your opinion on this, or what do you think here? So no, mostly because I wanted us to know about it before you watch the video, because if I just gave it to you at the very beginning, it might seem like gibberish. But now that we know a little bit about differential equations, I hope that you can kind of follow what they're doing. Like I myself probably couldn't like calculate everything that they calculate, but I can kind of get the idea of what's going on. So it's kind of like a little glimpse of like, if you took this further, here's some cool stuff you could do with it. So not required, but it's up there if you want to look at it. Because differential equations, are useful in so many different fields. I am not obviously an expert in all those fields, so I couldn't like actually come up with it. But when you get to high levels in a lot of places, these are really useful. One of the reasons that they make you take differential equations if you're going into like engineering or some of those other classes like that. So, this first one, we need to review quickly that if you see the word directly proportional, two quantities, x and y, are said to be directly proportional if x equals k times y, where k is the constant of proportionality here. So, I think we looked at this for something else. The best example of directly proportional would be if you're paid an hourly wage, it's the number of hours you worked and the amount of your paycheck, right? That should be directly proportional. If you get paid $10 an hour and you work 8 hours, then you would get $80, right? If the government didn't step in and take some of your money. But getting paid under the table, then that's what you would get. So, so it's just a number equals this constant times that other variable right there. So sometimes we will see problems like this. The amount of bacteria in the Petri dish increases at a rate proportional to the amount present. At time t equals 0, the amount of bacteria in the dish is 10 grams. At time t equals 2, the amount of bacteria in the dish is 30 grams. What is the amount of bacteria in the dish at time t equals 6? So a lot of stuff going on here. But you're going to start with that directly proportional expression. So amount of bacteria in the Petri dish increases at a rate proportional to the amount present. In this case, amount of bacteria in a Petri dish increases at a rate. So if we want like number of bacteria, they don't give us a variable to use. So like if we let B equal our number of bacteria, right? The amount of bacteria is increasing at a rate. What is that? What variables are we going to use for the rate that bacteria is increasing? dB, dt. Proportional, so that amount is proportional, so that equals, and it's just pretty standard to use a K, although you can use other letters for that. So K is some constant that we don't know, to the amount present. So that'd be the amount of bacteria present. What would we write for that? B. Okay. So before we do anything else, we need to solve this differential equation. Thankfully, it is not a terribly difficult differential equation right here. So I would start off by multiplying by dt. What can be a little confusing about this is that k is not a variable. K is a constant. So when you're integrating, you're not integrating with respect to k. B and t are your variables here. So we've got dB equals kb dt. So we need, the k can stay. The k, again, is a constant. It is not a variable. It can stay where it's at, but the b cannot be over here. It needs to be on the other side. So I'm going to divide by b. And so now I've got dB over b equals k dt. All right, so at this point, all of my b's are on the left. All of my t's are on the right. Even though that k is there, it's just a constant, so it's okay. So I need to integrate both sides. What do I get when I integrate dB over b? Natural log, absolute value of b. What do I get when I integrate k? kt. Because you have a dt on that side. And I need something else. What else is it? Plus c. Now, I think these problems are easier to do if you go ahead and solve them for the b in this case. So if I want to solve this for a b, I've got to get rid of that natural log. I'm going to do e to the power and e to the power. And so right here I just get the b. What do I get on the right hand side? What can happen with this c right here? It can become big and go out front. So c e to the kt. Does that seem familiar? Like something we may have done before in pre-cal? PERT. It's like the PERT formula. So this is really just continuous exponential growth. So if you have something growing at a rate proportional to itself, it's the PERT formula. And we're going to do a few more of these tomorrow. You can kind of just like already know that's what's going to happen, right? Instead of solving this differential equation. So we've got b equals c e to the k t. I need to find c and I need to find k, right, to make an equation here that I can use. So really this stuff we could have done pre-calculus, right? The solving of the differential equation we didn't know how to do, but if I told you it was continuous growth and you were using PE to the RT, then you could have answered this question earlier. So you want to start off with plugging in t equals 0 if you've got it. Because if you plug in t equals 0, then that is going to help you find that c pretty quickly. So bacteria is 10 grams, ce to the k, and the t is 0 right there. And k times 0 is 0. What is e to the 0? 1. So 10 just equals c. And you also kind of just know from doing PERT in the past that that c value is your initial value. So it ends up being 10. So now we've got b equals 10 e to the kt. Now we need to know k, right? Because b and t are our variables, so we don't need to replace them. So we need to know k. So I also know at time t equals 2, there's 30 grams of bacteria. So I'm going to do 30 equals 10 e to the k times 2. And I want to solve this equation for k. So Brady, what would I do to solve that for k? Good. That'll give me 3 equals e to the 2k. Next, if we're solving for k, natural log. We'll get rid of the e here. So we got natural log this side. I got natural log of 3 equals 2k. And Brady, what will we do last? Divide by that 2. So you can get a decimal for this if you want. I would just wait till the end so you don't have to round anything. So natural log of 3 over 2 is your k. So now our equation is b equals 10 e to the natural log of 3 over 2 times t. And so finally, we need to find the amount of bacteria when t equals 6. So what do we need to do at this point? Plug in 6 for t. So we got b equals 10 e to the natural log of 3 over 2 times 6. And this would be calculator active, where we could just type it in. So we got 10 e to the natural log of 3 over 2 times 6. And we get 270. Right.
Like time keep, like I thought, I don't know. But now
You could figure out this problem without doing all of this. Now, they don't always give you numbers where this would work. You got t equals 0 is 10. 2 is 30. They want to know 6 down here. Well, if I put 4 right there, like I multiplied by 3 here. I'd multiply by 3 again. That'd give me 90. Multiply by 3 one more time, 270.
Well, that's what I did, but I did like 10.
You added, yeah.
So I added 10, or I did like 2 times 10 plus 10 because it's 10 is 0.
Right.
And then I did 6 times 6, or 6 times 10 is 60 plus the extra
Yeah.
10 I got.
So you treat it, that would work if it were linear. But whenever you have like this directly proportional to itself, it ends up being exponential. So that's what we're kind of saying there. But what I just did here does not necessarily always work depending on like what numbers they give you. So definitely I want you to be able to do this. Okay. Newton's law of cooling is one of the coolest things that we do with differential equations. The rate, Newton's law of cooling states the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. And here, body doesn't have to be a dead body, but it is useful for dead bodies. So it could be any object. So Newton's law of cooling, I purposely left some space here because I want us to write it symbolically, right? So I am going to make capital, oh gosh, what's it doing here? I'm going to make capital T be the temperature of the body or the object or whatever you're studying here. I'm going to make capital T with a little a behind it, T sub a. I'm going to make that my ambient temperature. So that is like the temperature of whatever is surrounding it, right? Let's let lowercase t be time. You can use it for any units, so you can make it for minutes, hours, seconds. You just have to be consistent throughout the problem. If time is seconds in your problem in the beginning, it needs to be seconds all the way through. So if we read through this, the rate of heat loss of a body, what is that going to be? D big T over D little t, right? So D big T over D little t. That's the rate at which your temperature is changing. It actually works for temperature increases as well. But in this case, we're looking at heat loss. Is directly proportional to, so directly proportional to is where we do K times something. And it's directly proportional to the difference in the temperatures between the body and its surroundings. Typically, we do T minus T sub A. I think you could technically do it either way. It's just going to change what you're looking at here. This is usually used for hot things cooling down, and if they're cooling down, their temperature around them is lower than, so we usually see it written like this, although I believe it could work either way. Okay, this is Newton's law of cooling symbolically, right? The rate at which our temperature changes is directly proportional to the difference between our temperature and the ambient temperature. This means that, if there's a bigger difference, then you're cooling faster. Whereas if they're closer together, it's going to be cooling at a slower rate. So one of the very useful things that can be used here is this can be used for forensics. So if you have a situation as I have here, a dead body is found in a walk-in cooler in a restaurant at 6 a.m. when the first employee arrives. The cooler is kept at a constant 35 degrees Fahrenheit. When the body is found, it has a temperature of 72 degrees Fahrenheit. 20 minutes later, the temperature of the body is 65 degrees Fahrenheit. Estimate the time of death. Assume the person had a normal body temperature of 98.6 degrees Fahrenheit while alive. Okay, so this could be used to estimate time of death, which is a really important thing whenever you're trying to figure out who did it, right? This would be like if you were a forensic analysis, if you were an analyst here, this would be ideal conditions because the cooler's kept at a constant rate, right? Now, if the body is found outside and the temperature's changing or it was raining or, like different things were happening, that makes it more complicated. Also, once the body hits ambient temperature, you can't really use this anymore because it could have been an ambient temperature. It's not going to drop more. It could have been an ambient temperature for, an hour or a day or 10 days. So at some point you have to start looking at like the breakdown of the body. But this could be used, if you find somebody pretty quick, this could be used to figure out when the person died.
Could it be used for like if they're in like a heater, like an oven? Like opposite?
As long as it's kept at a constant temperature, then it should, yeah. It could, that could work, like that could be the case,
Yeah. Didn't that happen at Walmart not long ago? Like they found somebody in either the walk-in freezer or the walk-in oven. I guess it is the walk-in freezer.
Yeah.
Anyway, they found somebody dead. Yeah, I'm pretty sure, like in a Walmart.
In our Walmart or
No,
a
not
Walmart?
our-
Okay,
a-
okay.
That's what I
I was like,
in
in Elkin
a
Walmart.
different state.
Yeah.
Yeah, they found
That
somebody in
it.
the freezer.
I know that this has happened before. Like people have, like somehow, if something's defective, gotten locked in,
Yeah.
or
Walked in there.
yeah. I know Selena brought me a problem. She was in differential equations, so they were looking at harder problems. She had a problem where somebody had been killed outside the cooler and was drug into the cooler, and then so you have to do like a more complicated, analysis because they, But anyway, yeah. So, but we're gonna stick with this more simple scenario right here. So, if we look at Newton's law of cooling, then we got D capital T over D little t equals K times capital T minus, we know an ambient temperature here. What is our ambient temperature? 35. And it's not changing, so we can plug this in before we do our solving. So, if I want to separate variables here, I'm going to multiply by D little t. And I got D capital T equals K times T minus 35. D little t. Okay, my variables are not separated because I got this capital T over here. What do I need to do? Divide by that T minus 35. So I've got D capital T over T minus 35 equals just K dt. Remember here, just like the one we just did, K is not a variable, right? So your variables are separated. K is a constant. So capital T and lowercase t are your variables. Everything's separated. I need to integrate. So when I integrate here, what do I get? Technically, there's a u du right here. But what's the u is t minus 35. What's the derivative of t minus 35? You're like already going ahead and integrating. Derivative just t minus 35 is dt, right? So although there is technically like a u du substitution, you don't have to like multiply by 2 or 1/2 or anything here. So I would just go straight to natural log absolute value of t minus 35 right here, which is what Joshua said. Right there. And that will equal, what's my derivative of k dt? I'm sorry, integral of k dt? Kt plus c. And it will be easier to do this problem if we go ahead and solve this for the capital T. So we're going to have to do e to the power, capital T minus 35 is going to equal, what do I get over here on the right-hand side? C e to the kt right here. Go ahead and pull that c out as that coefficient like we can do. And then move that 35 over. So capital T equals C e to the k t plus 35. Okay, at this point you've done the calculus part of it. This is why Coach Wood could have you do these problems before you knew how to do the differential equation, because he just gave you the already solved differential equation instead of starting from the differential equation there. Now we are using T equals CE to the KT plus 35, and we need to find C and we need to find K, much like on the last problem that we just did. So if yeah, we're going to find C, then we'll plug it in, and then we can use that to find our K. Yeah, so we're going to go with the moment they're found as our initial time, right? So the moment they're found is going to be T equals 0. So this is going to be the point 0, 72. So we got 72 equals CE to the K times 0 plus 35. K times 0 is just 0. E to the 0 is 1. So you just end up with 72 equals C plus 35. So you subtract the 35 here, and that's going to give you 37, I think. Yeah. So now our equation is T equals 37 E to the KT plus 35. And we know 20 minutes later, the temperature of the body is 65. We could do this in hours or we could do it in minutes. It doesn't matter. Just know which one you're using. So I'm going to use minutes so that I don't have to do a fraction or a decimal for an hour, because if I do hours, I'd have to do 1/3. So I'm going to use minutes right here. So my T is going to be 20 minutes. My temperature of the body then is 65. So 65 equals 37 E to the K times 20 plus 35. And so I'm solving that for my K, and I'm going to do it kind of quickly because we're running out of time. Divide by that 37. So 30 divided by 37 is 0.8108. I'm going to keep that in my calculator because it keeps on going. Equals E to the 20K. What would I do next? Natural log. So if I do natural log of that number in my calculator, I get negative 0.2097, and that keeps on going, equals 20K. And last step for finding that K, divide by 20. Alright, so I got, I'm going to write down the whole decimal here. 0.1048600265 is my K. So T equals 37 E to the negative 0.0104 ... T plus 35. Okay, so I know it's about time if you want to be packing up while I'm showing you the last little bit of this here, because I want to know time of death so we can be on the lookout for the killer. So I'm going to use y equals 37e to the negative 0. 0.0104860.265 t plus 35. Okay, here's my graph. When was he alive? Or what was his temperature when he was alive? 98. That would be the capital T, which I've done as Y here, equals 98.6. I need to see where those two cross. Negative 51.65. So that person had been dead like 52 minutes. So you have came in very quickly on this murder, if it was a murder.
But their temperature was still kind of high.
Yeah.
Cooler like
So,
that.
and also, disclaimer, I made up these numbers and I have no idea how fast a body actually cools, so
In a 35
it might be unrealistic for a 35-degree cooler. I'd also say, like, it's important to measure for different people, because if you're, like, wearing a winter coat versus shorts and a t-shirt, or if you're super skinny versus a really big person, like, I think that's going to affect it. Definitely the clothing for sure. So.